Hello, everyone. Welcome to this wonderful conference and welcome to my talk on shopping recommendation. Sorry about the technical difficulty I have in logging. I'm Somnath Banerjee. I'm the engineering lead of the shopping discovery team at Pinterest. The mission of our team is to help users to discover inspiring brands and products that will help them to create a life they will love. Today, we'll get a glimpse on how we do that. Let's start with a stat. So currently, global annual e-commerce retail sales is $4 trillion. 30%, or almost one-third of that, comes from the recommendations shown on the e-commerce sites. The recommendations shown on the e-commerce sites are typically created by fully automated machine-learned recommender systems. I find it pretty fascinating to think that shopping recommendations generated by fully automated machine-learned systems are driving $1 trillion sales. In this talk, I will discuss how the shopping recommendations works in practice. The talk is divided into 3 sections. First, we will introduce you to how shopping at Pinterest works. Then we will deep dive into shop similar recommendations. And finally, we'll see when we have multiple different shopping recommendations and different page layout, how to put them together using a technology, what we call as whole page optimization. First, let's see how people use Pinterest. People come to Pinterest to collect inspiration and ideas. They collect images, videos, stories, and organize them into boards. We use the term pin to refer to image, video, or story saved on the user boards. The use cases varies a lot. The use cases varies from recipes, cooking, to travel, home decor, and many others. Here are some of the boards from my own Pinterest account. You can see my use cases are inspiration for kids, home decor, fashion, and many other things. But you can also see probably cooking is not my thing. The one interesting fact about these use cases are they often naturally lead to shopping. In fact, there is a study done last year by eMarketer which showed 40% of our users come to Pinterest to find or shop for products. This is 3 to 5 times higher than other social media like Facebook, Snapchat, and others. Let's see how a product shows up in our app. This is what we call is product detail page. It has all the product metadata like product title, price, the shipping information, etc. And also it has different shopping recommendations like more from this brand, price under certain, item under certain price, shop similar, which is the theme of the talk today. On the platform, we have tens of thousands of verified merchants. All major merchants in the category of home decor and fashion in the US are available in the platforms. Examples are Wayfair, Home Depot, and many others. But Pinterest is not a traditional e-commerce app. Shopping at Pinterest is quite different from other e-commerce apps. The way we think about shopping at Pinterest is a journey from inspiration to purchase. Users typically start with a broad idea, like set up living room. Then they go into finding inspiration or images about that idea. Then they go into the mode of learning their own preference, like what style they like, what furniture they actually will look good in their living room. Once they have found their preference, they go into refining those choices, like from which brand and price point to buy those products. And finally, they do the purchase. So this is a much longer journey, and this starts from a broader intent. Let's take an example. Here is our user Jenny from Brooklyn. She's looking to furnish her apartment. After collecting ideas and inspiration on Pinterest, she decided that she wants to buy a lamp. There are many different shopping entry points on Pinterest. One of the most popular one is what we call close-up. When Jenny taps into a living room scene or living room image to take a closer look, she finds all the objects in that living room image are tagged. Once she taps into one of those tags, like the floor lamp, she finds the shopping recommendations, which shows product very similar to the object that she has tagged. The other major entry point for shopping is search. When Jamie goes to search, she already finds that shopping spotlights or some shopping recommendation already curated for her based on her test. But she went ahead and puts the search query table lamps. Then she finds there is a shop tab. Once she taps into the shop tab, it shows the list of table lamps. They're all products from the verified merchant available for purchase in our geographic location. It also shows all the price, the brand, and other product information. The page also has some shopping recommendations like shop by this brand. Apart from this, Pinterest has some advanced shopping features like augmented reality based try on, where a user can try on a lipstick and see how they look on that lipstick. We also have skin tone filter, where the user can choose a skin tone of her choice and see how that looks. So all these features are great. We love this, but the real testament is the usage of this feature. And let's see how that is going. At Pinterest, we have 452 million monthly active users across the globe. This year, we saw 85% increase on our users who are using the shopping surfaces or shopping features. Shopping is today live in US and UK. And I put a couple of charts showing the growth this year, the shopping users growth and the shopping advertisers growth. So hopefully this gives you an overview how shopping at Pinterest works. Now let's switch gear and talk about recommender system. So recommender system has a very rich literature. It has been studied for more than 20 years now. There's a tremendous progress on the model, the machine learning model used in recommender system. Some names to call out: the collaborative filtering, matrix factorization. Also, these days, the deep learnings or deep neural networks are pretty commonly used model in recommender system. Recently, there are works on neural collaborative filtering. But in spite of all this progress, the recommender system is still an open and challenging problem to study. One open area is this massive scale of the problem. Today's recommender system has to predict for hundreds of millions of users from hundreds of millions of items. In some sense, it is fair to say the progress or the scale of the data has outgrown the progress in technology. Also, today's recommender system has to work out of many different data types. Back in 1990s, the recommender system used to work just out of the utility metrics, the user and item utility metrics. But today's recommender system has to work out of the user profile, text, image, video, and even graph. Today's recommender system has to optimize for many different objectives. There are different types of engagement, like clicks, long clicks, there's conversion or purchase. And also, it has to balance between the engagement and relevance, fairness, diversity, etc. And on any shopping site, there is not just one recommendation module. You will find there are multiple different recommendation modules. So today, we have to design multiple different recommenders, not just one. And when you have multiple different recommenders, different ways to lay them out, or different ways to display them, you have to put them together. That's what's called whole page optimization. In today's talk, I'll go into the details of soft similar recommendations, which will show you how you tackle the first three challenges that I mentioned. We'll also go into the details of whole page optimization, but we'll not talk about how to build different types of recommenders. With that, let's do a deep dive into shop similar recommendation. At the very core, the shop similar recommendation takes a query products and the user as an input and outputs a set of products that is similar to the query products and matches the user preference. If I do one level deep down, we'll see there are two core modules into shop similar recommendation. One is what we call candidate generator that takes the query product as an input and sometimes the user as an input and generates few hundred products candidate from a catalog of 100 million. So the role of candidate generator is to narrow down hundreds of millions of products to few hundred. Then the ranker takes those few hundred candidates and applies a sophisticated machine learning algorithm to select stock K candidates to display to the user. In practice, the recommender system has multiple different candidate generators. Traditionally, there are text similarity-based candidate generator, memboost-based candidate generator. But currently, with the progress in deep learning, what is working really well is the embedding similarity-based candidate generator. And let's see how that works. At the core of it, there is a neural network model which can take a product and create an embedding. And there is an offline workflow which goes over the catalog, takes each product and creates the embedding and store it in an embedding store. Then at runtime, at serving time, when the query products comes in, it flows through the same neural networks. Then we create the query embedding. We use that to do a nearest neighbor lookup into the embedding store and generate the few hundred candidate spins. So the key question is, how do you create a product embedding? I'll pause for a second here for you to think how to create product embedding. Maybe you are thinking there are various ways. That's right. You can just simply take the product image and put it into some standard neural network like ResNet or VGG and get the image embedding. Or you can do something even simpler, like use the word to wake on product title to create product embeddings. But at Pinterest, we use a very special way to create the product embedding. There are a few things that we like to use that we have in Pinterest is that one of this is our giant pinboard graph, and more about that in a minute. Then we have multiple data types, as I mentioned, like the image, the text, and the attributes of the products. We want to use all of those. And we have hundreds of millions of users in the platform who are engaging with our product. So we want to use all of the engagement data. And then we want to design the system that scales for billions of pins and also hundreds of millions of products. Here is a pinboard graph. So pinboard graph, as I mentioned, the user puts the pins in the board. We have seen that two pins in the board are similar. There are a couple of examples. One is kiteboard and one is snowboard. The pins in a specific board are actually similar to each other. So in the pinboard graph, two pins are connected if they are in the same board, and by virtue, they are similar to each other. So once we have the pinboard graph, we apply this graph convolution neural network on top of that to create the embedding of a pin or the node in the graph. There is a very seminal paper I linked in this doc, which came out of Pinterest. We use this technology across Pinterest, and we know that this is used across other companies as well. But at the very core of this, there is a very simple convolve operations, which works in iteration to create the embeddings of the pins. And how it works is embedding of a node at a given timestamp is defined as a concatenation of its current embedding and the weighted average of its neighbor embedding. So embedding of a node at a current timestamp is the concatenation of its own embedding and the weighted average of the neighbor's embedding. You can see there is a recursive definition here. So if you keep just doing the iterations, you will see the information from the far away nodes in the graphs will start flowing in. That's what brings the power of this algorithm, and that's what uses the graph. How do you use, So you can see there are some square boxes which are the neural networks. So those are the parameters of the graph. And we learn these parameters using our engagement data and standard triplet loss. And how do we use the image, text, and all other data types? So initial embeddings of the nodes are created using those image embeddings and the text embeddings. So it's initial embeddings are concatenation of the visual embedding and text embedding. There are many other innovations listed in the paper. Like, for example, we don't use the neighbors from the graphs. We actually do a random walk on the graphs and sample the neighbors. That's one innovation. There are many other scaling and innovation listed in the paper. I'll highly recommend you to read this paper. So now that I've shown you how to create the embedding and how to retrieve the embedding and create the embedding-based candidate generator, let's talk about how the ranking works. So ranker is a machine learning model which predicts a probability of engagement given the query and the user. But like I mentioned, there are multiple different types of engagement. How do we handle that? We use a multitask deep neural network to handle that. So at the input layer, we put all different features, and we have a technology called AutoML, which groups those features and crosses them each other. Then it flows through fully connected layer. And then we have these multiple different heads corresponding to each of the engagement, like close-up, clicks, long clicks. And those heads are predicts the probability of those engagement. Those predictions are calibrated and combined using a utility. And those combined, that gives us the final score based on which the products are ranked. Let's look at some of the results. So when we put this graph-search, this candidate retrieval, embedding this candidate retrieval, we saw 10% improvement in engagement. When we switch our ranker from the GBDT to DNN model, there was a 5% improvement in engagement. And when we changed our DNN, sorry, deep learning network model from single head to multi-head, we saw 7% improvement. So with this, let's talk about whole page optimization. As I mentioned, in today's e-commerce sites, you will find multiple different recommendations. Some examples are more from this brand. We talked about shop similar items under a certain price. Also, each recommenders can be used, can be shown, displayed using different recommendation titles. For example, the shop similar, you can call it more to shop, more like this, or many different ways. For each item displayed, there are different images to select. And then you can have different page layouts, like different color preferences, different types of buttons. So how do we put all these things together? We use what is called multi-arm banded approach. If you are not familiar with the multi-arm banded approach, don't worry. It is a framework which allows to do exploration and collect feedback or data. So in the multi-arm banded literature, there is something called arms or actions. And at any given point of time, the bandit has to select which arms to play. It can select the arms that it knows can give a lot of reward, so that it can exploit the arms, or it can select arms that it doesn't know much and it can explore that arm. So that is the classic explore-exploit trade-off. While designing a multi-arm bandit approach, for one thing to decide, like what are the arms to have in the system? Here is a simplistic view of the possible arms that we can have in our problem. So any given slot, we can have the arms. So a given slot, we have to place the module. So in our case, we can have the arms, like which module to place. So the modules for a slot can be an arm. For a given item, we have to select which image to display. So the images can be an arms for us. The module title, given a module, when you are trying to display which title to select. So the module title can be in arms. And different page layout templates are another type of arm. So this is a rather simplistic view. In practice, you might like to have combination of these as a one arm. So that will create a combinatorial number of arms, which is a challenge you need to handle. But let's just talk why we are using bandit approach, not just some learning to rank kind of approach. As I mentioned, bandit allows exploration to collect data in a more principled way and minimizing regret. And why we like to do exploration? Because there are combinatorial possibilities. Like if you want to rank just 5 modules, there will be a factorial 5 or 120 different possible rankings. You might not have data for each of these rankings, so you need to explore and collect data. You could have new modules wherein to explore. Mitigating bias is a big problem wherein to explore, collect new data. And there is an often shift in user population. At Pinterest, today we are seeing new users are coming, new demographic users. We are going live in different countries. So for all these reasons, we need to explore and collect data. Currently, where we are doing a number of experiments and we are seeing positive results. One positive result is we see that MAB, the multi-arm bandit-based model ranking, is performing better than the static placement. And we have seen like a 10% engagement improvement when we use the multi-arm bandit to select the item image. With this, I will wrap up my talk. So in summary, the shopping recommendation at Pinterest is using cutting-edge technology, like embedding this candidate retrieval, multi-head DNN model, whole page optimization. And above all, Pinterest is providing a unique shopping experience for the user for the journey from inspiration to purchase. It is possibly the only place where the users comes with a broad intent, find inspiration, and discover that will help them to create their life they love. With that, thank you all, and sorry for the technical difficulties at the beginning. Do I have time for a question? I cannot actually hear PJ, so I don't know if she's reading the question or not. Maybe I'll just read the question myself and try to answer. So, Cap, thank you for the question. You said if an arm is drastically performing bad, do you take it out before the test period? If yes, what happens to the traffic distribution? Yeah, if the arm is bad, we take it out. And I think, as I mentioned, the multi-arm bandit is a more principled approach. So we take it out when we feel there's a significance. We already have enough data to say it's a bad arm, it's a bad experience for the user. Okay. Thank you all. Have a good rest of the day. Enjoy the conference.